All right, let's talk about one of the most powerful, yet kind of invisible, forces that's shaping our modern world. It's like a hidden genius inside almost all of our technology, and it's called control systems engineering.
So to get started, here's a fun one for you. What on earth could a self-driving car, navigating a super complex highway, possibly have in common with that simple little thermostat on your wall? I mean, one is this pinnacle of cutting-edge robotics, and the other is, well, it's just a box that keeps your house from getting too hot or too cold.
Well, the answer is they both rely on that hidden genius we were just talking about. Something that is constantly measuring, checking, and correcting to make them do exactly what we want. Whether that's holding a perfect 72 degrees or, flawlessly merging into rush hour traffic.
And that hidden genius, it has a name: control systems engineering. You can think of it as the art and science of making any system, from the really simple to the unbelievably complex, behave exactly the way we want it to, every single time, predictably and reliably.
So what does a control systems engineer actually do all day? Well, their mission basically has three parts. First, they have to create a mathematical model of a system. Then, they analyze how that system is going to respond to the world around it. And finally, they design its brain, the controller, to make it achieve a very specific goal. Now, I know that sounds complicated, so let's use a simple analogy to break it all down. To really get a handle on this, let's imagine our control systems engineer is a master ship designer, and they've been given a huge task: create a brand new ship that can navigate any ocean on Earth totally safely and efficiently. This designer's whole voyage, their whole process, it always follows three crucial steps. First up, you have the blueprint. That's our model. Then there's the virtual sea trial. That's the analysis. And finally, building the helm, which is the actual design. Model, analyze, design. Remember those three. So let's set sail with step one, the blueprint.
Okay, phase one, the blueprint. Here's the thing: you just can't control what you can't describe. So before an engineer can do anything else, they have to capture the very soul of their system using the universal language of mathematics. It's literally like drafting the ultimate, most perfect blueprint for our ship.
And they have this incredible toolbox to get that blueprint just right. They can use something called bond graphs to map out exactly how energy flows through the ship, or they can use linearization to take a really messy, complex problem and simplify it into something they can actually solve. They even use system identification, which is kind of like taking data from a tiny test model to find flaws and make the full-size blueprint absolutely perfect. Now, engineers look at this blueprint in two main ways. The frequency domain gives them this big picture, high-level overview, kind of like an architect's beautiful sketch of the whole ship. But the time domain, or what they call state space, that's more like the detailed, moment-by-moment construction plan, showing how every single piece works together. You absolutely need both views to build a perfect vessel.
Okay, so the blueprint is done. It's perfect. Now it's time for the second and absolutely crucial phase, the sea trial. This is where we test our design against the brutal realities of the ocean to see if our ship is actually seaworthy. And the amazing part is, we do all of this before the ship ever even touches the water. The single most important question here is stability. In engineering jargon, that's just a system's ability to get back to normal after something messes with it. But for our ship, it's way more dramatic. When a giant rogue wave smashes into it, will it right itself or will it capsize? I mean, this isn't some academic question. It's literally a life or death test of our design. And that, of course, leads to the million-dollar question: how can our engineer possibly know for sure if the ship is stable before they spend $1 billion to build it and send it out into a real storm? The answer is just brilliant. They run virtual sea trials. Using these incredibly powerful mathematical tools like the Routh-Hurwitz criterion or Nyquist and Bode plots, they can create these super sophisticated computer simulations. It lets them throw every kind of virtual hurricane and monster wave at the blueprint to see if it holds up. And our ship passed. It made it through the virtual storms. It's stable. So now we get to the final and maybe the most active step, designing the helm. It's finally time to build the system that will actually steer our ship and guide it to its destination. This is where the control in control systems really comes to life. The controller is the absolute brain of the whole operation. In our ship analogy, it's not just the rudder that steers it. No, it's the navigation charts, and it's the captain shouting the orders, all rolled into one smart, automated system. And the most famous, the most widely used controller in the entire world is called the PID controller.
The P stands for proportional, and it acts like the helmsman's instant reflex to a big wave. The I for integral is like the navigator's logbook. It remembers all the past mistakes to correct the course over time. And D for derivative, that's the lookout in the crow's nest, forecasting where the ship is heading to prevent problems before they even happen. It's the past, the present, and the future, all working together in perfect harmony.
And beyond the trusty PID, engineers have even more advanced navigation charts. The route locus technique is like creating a map of every single possible path the ship could take in different conditions. And pole placement? Whoa, that's even more powerful. It's like letting the designer point to a spot on that map and say, I want the ship to behave exactly like this. The level of precision is just incredible.
So we've taken our ship on its entire journey. We created the blueprint, we put it through sea trials, and we designed its helm. But the real magic of this whole field is that this exact same three-step process, it doesn't just apply to ships. It applies to, well, pretty much everything.
This three-step voyage is happening all around you, right now. It's in medicine, guiding automated drug delivery systems. It's in the robots on an assembly line, making sure their movements are precise. It's what keeps an airplane stable in turbulence, what keeps a chemical plant from exploding, and what keeps your car's cruise control perfectly steady. It is the hidden genius running the show behind the scenes of our entire world.
And all of that mind-blowing modern technology, it all comes back to three simple, elegant, and incredibly powerful steps that engineers use to bring order to a chaotic world. Model, analyze, design.
So, if engineers are already using this exact three-step process to steer a rover on the surface of Mars from millions of miles away, it leaves us with one really fascinating question to think about. What will they be able to control next?